let's solve this system of differential equations. We have d dt of the vector x equals matrix 1, 1, 3, 4 times the vector x. And our vector x is right here, contains x1 and x2. Now I'm going to use eigen analysis to solve this problem. But first I'm like to write this up in a more friendlier way where I can see it better. What do we have? This x prime equals ax, that translates this into this, and if we fill in our x's from here, we can write it up that x1 prime x2 prime equals the matrix didn't change and times our vector, which is x1 and x2. First up, we need to find our eigenvalues. This is what we need to solve in order to find them. The determinant of the matrix A minus lambda times the identity matrix equals 0. We plug in our matrix A from here. We plug it in minus the lambda, which we have to subtract on the diagonal, because we're multiplying with the identity matrix, right? Okay, here it is, plugged in, equals 0. Solve this determinant, this times this minus this times this. That's what we see right here. Clean it up, and we're able to find a quadratic equation of lambda squared minus 5 lambda plus 1 equals 0. From here, we're able to find the roots of this equation. That's going to give us lambda 1 and 2. 5 plus minus square root 21 over 2. And these will be my two eigenvalues for this problem. Now we could continue and turn these into decimal form, which would be just fine, and we could continue the problem that way. But I'm going to leave them in this form because later on I'm going to show you a shortcut where leaving it in this form will help us out quite a lot. For each eigenvalue, we will have to find an eigenvector. Okay, so for my first eigenvalue, lambda 1, I'm gonna use 5 plus square root 21 over 2. And let's find this eigenvalues eigenvector. Here's the equation that we need to solve in order to find our eigenvector. This lambda 1 will be plugged in right here. There it is, filled in. My matrix A minus lambda on the diagonal, right? This is my x vector, x1 and x2, equals the 0 vector right here. Clean these two up. Right here we can see negative 3 minus square root 21 over 2. 1 stays unchanged, 3 stays unchanged. And here 3 minus square root 21 over 2. These two stay unchanged for now. For the next step, I'm going to transform this into equations right here. This times this plus this times this equals 0. That's this 0. Now for the second line, this times this plus this times this equals 0. That was the second line. Now I'm going to determine if these two are multiples of each other. Therefore, I'm going to take the first equation, solve for x2, plug it into our second equation, and simplifying, we can see that we're going to get to 0 equals 0. Very good. That shows us that these two are multiples of each other. Therefore, we can ignore one of them and just work with this one. Now to solve for x1 and x2, we will simply pick a value for x1. I'm going to pick x1 equal 2 because when I plug it in here, this 2 will cancel out. Therefore, my x2 will look a little bit prettier, 3 plus square root 21. Now, remember that here we can pick any kind of number, right? We have infinitely many solutions. Therefore, you can pick 1, 2, 10, 11, 67 million, whatever you like. Just pick something that's not too crazy. And then write up our vector. X1 vector will be 2 from here and 3 plus square root 21 from right here. This is my x1 vector. Now we're going to have to follow the exact same process and work with our eigenvector, our second eigenvector, 5 minus square root 21 over 2. We're going to write it up and follow the exact same steps that we used for our first eigenvector. Right here, we turn it into equation form, then check, make sure again they are multiples, 0 equals 0, very good, they are multiples of each other. And to find our solution for it, again, we're gonna have to guess, just pick a value. I'm gonna pick 2 again for my x1, plug it in, and I'm able to find my x2 being 3 minus square root 21. Again, same just like in the first eigenvector, we can pick anything we want. And to finish it up, our x2 vector, 2 comes here, this comes right here, and there it is. Now for the final step, we are able to write up our general solution. X vector equals C1e, the first eigenvector, times t, and eigenvalue, sorry, this is the first eigenvalue times t, then the first eigenvector, then plus C2e with the second eigenvalue t, and the second eigenvector from right here. Now sometimes we could be asked to write it up individually. X1 would be this, x2 would be this right here. We simply, for x1, we would take this, and only the top. Again, this, and only the top. For x2, you would take this, with the bottom, plus this, and the bottom again. That's how you would write them out separately. Now, let's take a look back where we came from. This is at the beginning when we started. We found our eigenvalues, right? We found these two eigenvalues. We found 5 plus minus square root 21 over 2. And we said we could go ahead, turn it into decimal forms and follow the same steps we just did. But sometimes it's better to leave it just like this, because these are radically conjugate roots, right? We could have complex conjugate roots. These are radically conjugate roots. We have this plus minus. So we could take a little shortcut, find our first eigenvector just like this without any change. And when we get here, we have 2 and 3 plus square root 21. Since we have eigenvalues that are radically conjugate, all we have to do, instead of doing all these calculations again for the second eigenvector, simply change our sign in our vector. Since they are radically conjugate, this is possible and significantly reduces our work. Now, I'm pretty sure that you guys noticed that the solutions for these problems can always end up looking different from one person to the other one. Therefore, here it is, solved again, where the solution ended up with different values in it. Now, this, remember, it always changes because from here, as we calculate, till here, nothing changes, all the same. But here, where we need to decide what value we pick for x1, and therefore we're gonna get x2, this will vary from person to person. Therefore, here I picked x1 to be 1. And there you go, my x2 will look differently. Therefore, my vectors will look differently. Therefore, my solution, when it's filled out, will look differently. So, don't be alarmed just because it looks different. Make sure that the proper steps are followed, and therefore you end up with a, even if it's different, but still correct solution. But generally, it will still have the same structure, right? We will still have c's, the constant, we will have e to the power of the eigenvalue, we will have the t, and we will have the vectors. And there it is. Thank you for watching. Please give a like to the video so other people can find it as well, and have a great day.